The idea of this video is it should serve as a comprehensive way of digesting the technical details of this paper. In the video description below, you'll find a table of contents with timestamps, and that'll allow you to skip directly to the portions of the video that you're interested in. As you may have guessed from the title, this work is about time reversal optics. But I'm actually going to start with time reversal water waves because they're pretty straightforward to visualize. Here we have a tank of water. We disturb the water by dropping in these logos, and the waves from that disturbance propagate out towards the boundary of the tank. Now imagine the walls of the tank have the ability to record the waves and can then vibrate to recreate those waves in the time reversed order. In doing so, it will create the time reversed wave, which will propagate as if we're watching a video of that original disturbance in reverse, until it ultimately recreates the indent of the logos at the instant they hit the water. This is a pretty simple example, but the same idea holds even if there were other objects and obstacles in the tank, as long as they don't absorb the waves. And we're also ignoring things like friction, etc., right? Obviously, we can't recreate a wave that we never observed at the boundary because it was absorbed internally. An alternative approach is to use a transfer matrix method. So you could drop a relatively simple object like a ball into the tank from every position and then measure the waves generated for each of them. So these balls are like our pixels, and all possible patterns are just superpositions of waves we've already measured for the various positions. So the advantage here is that you don't need to have access to a physical copy of the potentially complicated pattern you want to generate, which could be a task unto itself. It also means that once you've measured the transfer matrix, you have all the information you need to do anything. You don't ever have to do another measurement. So it's actually quite a powerful way of going about it. So this type of control has previously been demonstrated in water waves. I've got some examples here. Top left is an actual time reversal type demonstration. I suspect the other two would probably have been calculated analytically or numerically, but the results and the principles are much the same. It's about the ability to either physically measure or numerically calculate the waves you need to produce at the boundary of the tank and then actually generate them in practice to create the desired patterns at the desired times. Now let's look at acoustic waves, which is actually where a lot of this research started. Here we've got a room where ideally all the walls, ceiling, and floors are microphones. At the center of the room, a sound is made, the wave propagates out towards the boundary where it's recorded at all positions. That recording is then reversed and replayed through the speakers from all positions, and in doing so creates the time-reversed acoustic wave, which propagates back into the horn just as it started. For radio and microwaves, the same idea applies, except now instead of speakers and microphones, we've got antennas. The source wave propagates out, it's recorded, flipped in time, and then replayed from all positions to recreate the original source. These time reversal principles have previously been demonstrated in acoustics and microwaves, as well as the water waves we already saw. It's certainly a neat trick, but it's also much more than that, because creation of these time reversed waves is really like the ultimate form of wave control. Because if you can measure and control all the wave properties in both space and time, then you can deliver those waves to locations in ways that would otherwise be impossible. Let's say we've got our scattering object here. If we're talking about optical waves, it could be something like a frosted piece of glass or an optical fiber or smoke, fog, biological tissue, something which scatters the waves but doesn't absorb them. If we try to inject a traditional wave into the object from the outside, it quickly becomes scattered near the surface. Right? We can't focus the wave deep inside the object. However, if we create a time-reversed wave, it can behave as if the source originated inside the object itself and then propagated out. So you send in the time-reversed wave, which looks pre-scattered, and then the scattering inside the object itself is what focuses it. And this is actually the context in which time reversal was first demonstrated, using time-reversed acoustic waves to destroy kidney stones inside the body from the outside. So if we have a light beam, an optical wave, it comes in from the source, gets scattered, and we'd like the ability to record that and then replay this light wave in reverse like we could for water, acoustics, and microwaves. But that's not previously been possible. Water waves, acoustics, microwaves, these waves have carrier frequencies and bandwidths on the scale of like hertz to gigahertz, which means you can record and generate such waves using electronics, digitizers, arbitrary waveform generators, etc., directly in the time domain. But with optical waves, we're dealing with carrier frequencies in the hundreds of terahertz, and often bandwidths as well that are many terahertz. So well outside what even pretty fancy electronics can handle directly. In optics, we don't have that nice direct access to measuring and generating the waves in the time domain like you do for the lower frequency EM waves and acoustics. For the past 10 years or so, there's been a lot of research working towards time reversal in optics. It kicked off with spatial-only control for focusing monochromatic light through a scattering media by wavefront shaping. The first paper really on this topic was this one. It used an iterative approach. A spatial light modulator at the input was updated iteratively based on feedback from the output side until a focus was created. So attacked more as a general optimization problem rather than by backpropagating waves, but inspired by the previous work on time reversal in other wave phenomena like acoustics and microwaves. Another very influential paper in this field is this one, which introduces the transfer matrix-based approach to optics. That is, you launch in a set of orthogonal inputs, measure the corresponding outputs, and construct the transfer matrix, which encapsulates the linear relationship between the input and the output. I've shown the input basis here as focus spots, which is a pretty common basis choice nowadays, although in this specific paper it was actually a Hadamard basis. Now, with the transfer matrix measured, we can map any spatial input to any spatial output, and hence you can focus through the medium to any position without ever having to actually physically backpropagate the focus spot you want to regenerate, as well as also generate all kinds of other patterns, more complicated patterns. So in this case, you phase conjugate the matrix itself rather than physically measuring the phase conjugate of a backpropagated beam. This is all spatial-only control. The wavefront going in is controlled only spatially, not temporally. The light source is monochromatic or narrowband. However, the scattering process itself is spatiotemporal. It's not just spatial. As the light scatters, it's being constantly coupled and redistributed amongst many different spatial paths. Those different spatial paths have different beam shapes spatially, but they also have different path lengths, meaning they arrive with different delays. The light might come in at a single position at a single point in time, but it'll come out the other end at many different positions at many different times. And if the impulse response has features in time, that means its Fourier transform, the frequency response, isn't flat, and that means it's got a wavelength dependence to it. If we only have spatial control and we move away from the center wavelength, our focus or whatever our pattern is, will decorrelate, won't work anymore. To compensate for that, you'd need the ability to generate a wavelength-dependent speckle pattern, which if you've got all the phases correct, also means you'll be creating a spatiotemporal beam. Now the scattering medium itself couples the spatial and temporal properties together. So how you launch a beam into the medium spatially affects not only the spatial properties of the beam at the output, but it also affects its distribution in time. And there's been a lot of different demonstrations over the years of various combinations of partial spatial and partial temporal control. So various combos of like controlling input space to control output space, input space to control output time, polarization control is in there sometimes not. I mean, there's too many combos to go into all of them here. So I'm going to take a step back. Let's forget about the scattering medium itself and just look at the type of beam control people have implemented. So what kinds of beams can people actually generate and control directly at the input? So what knobs do we actually have access to? First up, there's spatial-only control. Typically, you've got something like a spatial light modulator, an SLM, and that lets you create a beam that's some arbitrary 2D function of space, X and Y. And that's by far the most common type in this area of research, I'd say. You've got two dimensions of control, and both of those dimensions are spatial dimensions. Next up, you've got some sort of temporal pulse shaper, either implemented in frequency domain or on slower timescales in the time domain. That's just one dimension of temporal control. And you could use that in series with an SLM, like I just mentioned, and you'd be able to generate a separable function of space and time. You can control the beam shape with the SLM, and you can apply a pulse shape to it with the pulse shaper. But it's separable. The beam shape is the same for all arrival times. In this diagram, I've got a Hermite-Gaussian spatial mode that's a rectangular pulse in time, for instance, but it could also be a more complicated pulse shape. So this is control, and I'll call it like 2+1 dimensions. It's not full arbitrary spatiotemporal control. You can't make different beams arrive at different times. Then we've got something like this, where there's one dimension of spatial control and one dimension of temporal control. An example of this is a traditional spectral pulse shaper with a spatially multi-mode beam. So one axis of the SLM is used for frequency control, and then the other axis can shape one of the two spatial axes of the beam. The other axis, the other spatial axis, is shared with the frequency axis on the SLM. So for that axis, you can't independently control space and time. They're the same knob. It's still just two dimensions of control on a single SLM, but organized in a different way. For time reversal, in the general case, you need three dimensions of control. The ability to independently control the impulse response of every spatial and polarization component. Let's not forget that polarization exists. That's full control, like we've got shown here. A completely arbitrary, potentially quite complicated function of 2D space and 1D time. All right, so how could something like this be achieved in optics? In acoustics, microwaves, water waves, they've all used time domain approaches. For optics, at relatively low bandwidths, you could attempt a time domain implementation, which would end up being a little bit like a specialized variant of a mode division multiplexing system in telecommunications. Arrays of coherent receivers for measuring this full spatiotemporal field, arrays of Mach-Zehnders for generating arbitrary spatiotemporal fields. Now, there's a lot of technical details in terms of you'd have to match all the path lengths, phase stabilization, driving so many Mach-Zehnders with independent and synchronized electrical waveform generators. It'd be tricky and be pretty expensive, but it would be possible. The bandwidths, though, are ultimately going to be electrical domain sort of bandwidth, so tens of gigahertz. You could get fancy and you could start trying to do like spectral slicing techniques to increase the bandwidth, but the complexity is really going to start to balloon pretty fast. So for example, to do the 4 terahertz of bandwidth and 90 modes that we demonstrate in this work, you'd be talking about 80,000 10 gigahertz modulators driven by the same number of arbitrary waveform generators. So not great, certainly very complicated. And of course, that's why pulse shaping at these large optical bandwidths is typically done in the frequency domain, not the time domain. And that's what we'll be doing here. Also, probably importantly, a lot of the applications where an optical time reversal system would probably be of interest are working with optical sources anyway, like femtosecond lasers. So those systems, they've got an optical input, it's not electrical. So it's not just a matter of it being a pain or it being complicated to have an electrical drive. You also just actually wouldn't want it. You want to drive it optical. However, I do think the time domain approach, even with just like 10 or 100 gigahertz of bandwidth, would still be a pretty cool device. It'd just be quite different in terms of its application space. And I think importantly, science-wise, quite difficult for other labs to duplicate without spending a lot of money. Okay, so here we have a schematic of the device that's the core of what we're demonstrating in this work. It's a polarization-resolved, multi-port spectral pulse shaper in combination with a multi-plane light conversion system, an MPLC. The MPLC implements a 1D to 2D spatial transform, which I'll talk about in a bit. This device is a single SLM design, and programming the phase mask on that SLM allows you to control the impulse response of the first 45 Hermite-Gaussian spatial mode components in both polarizations. That is 90 spatial and polarization components total. You can think of it like this. The spatiotemporal field we want to generate is encoded in the SLM's phase mask, which scatters the light, redistributes the light along the X and Y axis of the device, and in doing so, it's redistributing the light in space and in time. And hopefully that will become a bit clearer in a moment. So let's take a look at specifically how this thing works. First up, I'm going to simplify the schematic a bit. Remove things like turning mirrors, relay optics, wave plates, polarization diversity optics, bits that you do need in practice, but which don't really help you understand how the device works. Just take a look at the key components. We'll mostly be illustrating just a single polarization component, but there's actually two sets of beams throughout most of the system, one for each polarization component, but the idea is the same for both polarizations. Light comes in from the source. 3 cylindrical lenses image the input spot onto the grism along one axis and collimate the spot along the other axis. Through the grism, the beam then travels through 5 cylindrical lenses, which conceptually are doing the job of just a single lens, really. They're just the Fourier transform with some additional resizing in X and Y. On the SLM, we have our spectral components, which have been dispersed across the X-axis by the grating. The device operates in the wavelength range 1535 to 1570 nanometers, which is about 4 terahertz of bandwidth, and which means we can address temporal features down to about 230 femtoseconds. Each spectral component is about 3 pixels wide on the SLM. So if you just put CW light in, that's how big the beam would be on the SLM. And each pixel corresponds with approximately 5 gigahertz, meaning we can address the beam with a resolution of around 15 gigahertz total. Along the y-axis, the beam roughly fills the height of the SLM to maximize the number of spatial modes we can address. And more about that in a moment. Remember, this is just one polarization component. There's also the other polarization component, which is addressable on the other side of the SLM. The beam reflects off the SLM, back through the cylindrical lenses, and onto the grating, where now we're in the Fourier plane of the SLM. So by putting a phase tilt along the y-axis, we'll be steering the spot up and down on the grating. This is how we'll be addressing the spatial modes of the system. Different positions along this y-axis correspond with different Hermite-Gaussian modes on the output beam side. This is a single y-axis, but it actually corresponds with 2 spatial axes in the output beam side through that 1D to 2D conversion that the MPLC does, which I'll talk about in a bit. The x-axis is the time axis. So steering along the x-axis creates delay. Taken together, by controlling how light is distributed in X and Y in the plane of the grating, we're controlling the spatial and the temporal properties of that output beam. Alright, if we're applying a linear phase ramp along the x-axis of the SLM, and the x-axis of the SLM is the frequency axis, then we're creating a frequency-dependent linear phase shift, which is what delay is. So mathematically, we know we must be creating delay somehow. But if you take a look at the optical system from the top, you can see how that delay physically manifests, where it actually comes from. When we steer along the time axis, the light is taking a longer or shorter path back through the grating, which is where the delay, is physically coming from. Okay, back down to the plane of the table. For a given phase mask on the SLM, we end up with a field like this near the grating. One axis represents how we want the output beam to be distributed in space, and the other is the time axis, which represents how we want the output beam to be distributed in time. Propagating back through the system towards the MPLC, we end up with this 2D light sheet. One axis represents space. It represents the beam shapes we want to generate, and then the other axis represents the times at which we want to generate those beam shapes. This light sheet's like play a piano roll or sheet music, where instead of the piano keys representing the notes we want to generate, they represent the beam shapes we want to generate. We've got a discrete finite number of shapes to choose from, the first 45 Hermite-Gaussian modes, and the light sheet specifies what combinations should be played at what times. That light sheet is fed through the MPLC system, which converts the 2D sheet into the corresponding 3D beam, with the desired wavefronts arriving at the desired times. In this example here, it's generating a clock hand of light, which is spinning around in time, which when you look at it all at once like this, like we're doing here, looks like a piece of corkscrew pasta. It's an ultra-fast wavefront shaper. It can spit out a sequence of independent wavefronts separated by a bandwidth-limited amount of time. which for us is about 230 femtoseconds, for a duration of about 20 picoseconds. So about 85 frames displayed at 4.3 terahertz. The MPLC part is critical here. The way it maps a 1D array of spots to a 2D set of Hermite-Gaussian modes lets us address 3 dimensions of control in the output beam, 2 space, 1 time, using only the 2D surface of the SLM. So looking here, as the light sheet is fed in, it propagates through the 14 planes of the MPLC to generate the desired output pattern. Each input spot on the left becomes a specific Hermite-Gaussian mode, which when you sum them all together over time creates that clock hand beam at the output. Now for the time reversal demonstrations, we'll be generating beams like this at the end of our scattering media, which is a multi-mode optical fiber. So you wouldn't be generating the clock hand directly at the end of the MPLC. You'd be generating it, some random looking scattered field, which would then become the desired output on the other end. But I'm showing it like this because it's clearer as a demonstration. One of the good things about working in the Hermite-Gaussian basis as opposed to an array of spots is also that it means that we don't have any dead space in the beam, either in the near field or the far field. We can address any position, whereas obviously if you had an array of spots, there'd be certain places where you just can't deliver light because there's no spatial mode there. You can also think of it as an extension of traditional holography to include an additional dimension. Instead of a traditional hologram, where you've got a 2D diffractive element, which encodes a 2D wavefront, which in turn can correspond to the surface of a 3D object, here we've got a volumetric diffractive element, the SLM itself, the grating, the MPLC, which has encoded in it a volumetric wavefront, 2 space 1 time, or 3 space if you want to think of it like that instead. This device allows a new type of optical control, complete control over all light's classical linear properties simultaneously. The ability to generate completely arbitrary vector spatiotemporal beams. So of course it's got all the linear time reversal type applications that have previously been demonstrated in other wave phenomena, the ability to spatially and temporally control the beam after propagation through a scattering media, and that's the main context we'll be demonstrating the device in here. However, this device could also have a lot of applications that are specific to optics, applications that aren't just generalizations of phenomena that we've seen before for acoustics and microwaves. Particularly to do with light-matter interactions and nonlinear phenomena. So for instance, particularly in the context of multi-mode optical fiber, you could use it for amplification, disperse the beam spatially and temporally at the input on the low power side in such a way that the scattering along the length of amplification creates the spatiotemporal focus only at the output, in either the near field or the far field. Again, particularly in multi-mode optical fiber, there could be all kinds of new nonlinear phenomena, spatiotemporal solitons, spatiotemporal mode locking, either by injecting the spatiotemporal beams into nonlinear fibers single pass, or as part of the feedback loop itself, tuning the spatiotemporal properties of the cavity to create new laser types. And remember, for all of this, we've got polarization control on top of everything else. So particularly for high NA applications like micromachining, microscopy, trapping, coupling to nano antennas, plasmonics, metamaterials, you could sculpt the spatially dependent polarization for every delay or every spectral component. So these are new types of beams, allowing you to sculpt light through the focal volume in new ways that wouldn't otherwise be possible. So hopefully there's a lot of new stuff you could do with this. As it means now, if you theoretically require some arbitrary distribution of optical field in space-time, amplitude, phase, polarization, the lot, you can actually generate that now. The ability to arbitrarily shape a beam in space with an SLM, or arbitrarily in time with a spectral pulse shaper, both opened a lot of doors, respectively, so we'd hope this new ability for arbitrary control of space and time simultaneously could also be quite widely used. Now, just for completeness, before moving on, I'll go over the schematic itself in detail. Light actually enters here from the source, goes through a PBS and a mirror. Now we've got the two polarization components as separate beams. There's wave plates to line up the polarization with the grating and then also with the SLM. There's a mirror here, just to fold the beam and keep the system compact, doesn't do anything else. Like I alluded to earlier, there's 5 cylindrical lenses, but they're ultimately just doing the Fourier transform in X and Y. So you can really just sort of think of them as one lens. But it's split up amongst multiple lenses to reduce aberrations, to do some resizing of the beam, and also to give you some flexibility in terms of how you want to adjust the parameters a bit when you're actually gluing this thing down. Then back through the system, it's basically just as it was through the animation, except we've got the polarization diversity optics in there now. There's a pick-off mirror here that sends the beam towards the MPLC system rather than back into the input source. There's a lens relay between the MPLC and the spectral pulse shaper sections, just because they physically sit on apart on the table. Then we've got the MPLC, which gets coupled to a multi-mode fiber, which isn't shown in the 3D diagram. This is a photograph of the optical system. Inputs over here, SLM's over there, goes off to the MPLC through the lens relay, and through the MPLC to the multi-mode fiber. Now I'm going to talk about the characterization and generation procedure. We'll be using a transfer matrix-based approach here to generate completely arbitrary spatiotemporal fields at the end of a multi-mode fiber. Fiber itself is a length of OM3 fiber, so that's a 50 micron core graded index multi-mode fiber, standard kind of fiber used in data communications. It supports 45 spatial modes per polarization at 1550. So we can address all spatial and polarization modes across the entire delay spread in the fiber. So that means there's no scattering process through this fiber, which our system can't undo. There's two parts to this. First, measurement of the transfer matrices, then generation and verification of the desired patterns. This is the summary of the transfer matrix measurement procedure. Our device works directly in the frequency domain, and that's also the domain that we'll be characterizing and verifying it in. We'll be using swept wavelength digital holography. The source, swept wavelength laser. One path from the source goes through the device itself, and the other becomes the reference arm for the digital holography, which is how we'll be measuring the spatial optical fields. The SLM steers to each input spatial mode in each polarization, one at a time, for a total of 90 modes. We can see that spot gets transformed into the corresponding HG mode through the MPLC here, which is coupled into the multi-mode fiber under test. And then for each of those modes, measurements are being taken as the frequency is being swept by the laser. The mode goes into the fiber, gets scattered, and then shows up at the other end as some different optical field, a superposition of a bunch of spatial and polarization modes. The facet of the fiber is split into the two orthogonal polarizations and imaged onto the camera, where it's interfered with the reference beam. Then we reconstruct the optical field using off-axis digital holography. That gives you the field in the basis of pixels, but we store it in the basis of the modes of the fiber. So for every frequency sweep, we get something like this: the amplitude and the phase of every spatial and polarization mode at the output as a function of optical frequency. For transforming that, you can also look at it in the time domain. So in total, you get this data cube, a 90 by 90 complex matrix, which describes the amplitude and the phase of the couplings between every pair of input and output spatial and polarization modes as a function of either optical frequency or of time. So that is, we've got a complete linear description of the system. There's nothing else left to measure about its linear properties. We can map anything to anything for all modes in either directions in both the time domain and the frequency domain. One of the good things about frequency domain characterization is it gives us plenty of dynamic range for looking at the results in both the frequency and time domains. So ultimately, we'll be demonstrating spatiospectral beams, where we target specific spatial beams at specific wavelengths, as well as spatiotemporal beams, where we target specific spatial beams at specific delays. Then comes the fun bit. Because we've got that full linear description, we can now make any spatiotemporal field at the output of the fiber within the limits of the optical bandwidth and the frequency resolution. We take the desired output spatial states as a function of frequency and backpropagate them through the fiber using the transfer matrices as a function of frequency. And that gives us the required input states as a function of frequency. The corresponding phase mask is calculated using a Gerchberg-Saxton algorithm to generate the required amplitude and phase for each mode at each wavelength in the plane of the SLM, which corresponds with the required amplitude and phase for each mode at each delay in the Fourier plane at the grading. The mask is displayed on the SLM, and then we do a characterization sweep to verify. The example illustrated here shows that ticking clock hand beam, which I've been using as an example, shown here in both the frequency domain, where it doesn't look like much, and the time domain, which is really the target domain for that demo. So when this experiment was first conceived, the idea was that we do a relatively simple demo, like backpropagate a spot or some spatial pattern generated with an SLM, possibly with a single mode spectral pulse shaper attached in series to give us a little bit of temporal control, measure the field either at the input SMF or with digital holography somewhere else in the system, then forward propagate to regenerate. But then we were like, wait, why are we even bothering to backpropagate? We're not trying to prove that time reversal symmetry itself holds for optics or anything. That's a given. We're demonstrating this new kind of optical device and trying to accurately characterize its performance. There'd be some applications where we'd expect this device to be of use, like nonlinear optics, where backpropagation wouldn't even be an option because there'd be isolators in the system. But probably more importantly, if we go that extra step to get the transfer matrices, then backpropagate the desired spatiotemporal states numerically, we can not only generate relatively simple stuff like spatiotemporal focus. People have never generated that through a scattering media or anything before, but that's a pretty standard type of beam in a general context like free space. So we could not only generate these old types of beams in new ways, like through a scattering media, but also just straight up generate entirely new types of optical beams that have never even existed before in any context, like that ticking clock hand example, but also a bunch of other crazy beams we'll be getting to in a moment. They're not just new in a scattering media context, they're also just new in any context. I won't go into the calculation of the masks in too much detail. There's nothing particularly special about it. It's just a Gerchberg-Saxton type algorithm with a single phase mask. It tries to generate the correct amplitude and phase for each spot in the 1D array of the MPLC input at the correct delays. And it employs a don't care dump region to ensure the correct amplitude and phase in the area of interest, the spot array, at the expense of discarding some light elsewhere. This mask calculation procedure isn't specific to this device, it's just a general problem of trying to generate a desired complex field with a single phase mask. I will quickly take a look at an example, however. This is actually an example we'll look at in a bit to test the delay-dependent loss of the device. At the output of the multimode fiber, we're generating a horizontally polarized spot at 0 picoseconds and a vertically polarized spot which is changing in delay. But for the purpose of this, it doesn't actually really matter what it is. All you need to keep in your head is that the SLM is trying to generate some superposition of spatial and polarization modes that are grouped around delays of about 0 picoseconds plus another delay which is going to be changing. Here on the left, we're looking at just one of the polarization components in the SLM. There's the phase mask itself, represented by the colors, and there's also the illuminating source beam, which is the Gaussian roll-off we're seeing in the top-down direction. So that's where the light is actually hitting the SLM. X-axis is the spectral direction, and then the Y-axis is the steering direction, the spatial direction. We specify the target we want to generate in the spectral domain, which is what we're looking at here in the middle panel. X-axis is frequency, Y-axis is spatial location. What we have is a distribution where different spots in the 1D array input to the MPLC are being excited with different amplitude and phase as a function of frequency. It's got a region of interest where the 45 1D spot array is, and it's got a don't care region outside of that where light is discarded. And it's discarded in order to ensure good beam quality with the right amplitude and phase in the spot array. This spatiospectral plane doesn't physically exist anywhere in this system. The spatial axis is in the Fourier plane of the SLM, but the spectral domain is in the same plane as the SLM. So this is just a computational plane in which we define our target. It doesn't actually physically exist anywhere. You can also specify the target in the time domain. That also works. If we were using a two-plane SLM approach, which I'll talk about a bit later on, this spatiospectral plane would actually be the plane of the second SLM, and the need for don't care regions would also be greatly reduced. Again, all of this is just a general property of spatial mode conversion using multiple planes. It's not specific to this device. Next plane here is effectively the plane of the grating, or near the plane of the grating, because the grating is actually tilted at an angle with respect to the SLM. It's the time domain. X-axis is time, Y-axis is spatial location. We've got superpositions of modes being generated at different delays. And in fact, even just by eye, you can see a bit of what's going on. As we change the delay, the spatial frequencies on the SLM increase in that X direction, left to right, also in the spectral domain, and we can see the corresponding delay generated in the time domain. Now comes time for some actual measured results. We'll be demonstrating both spatiospectral beams, where different spatial and polarization states are assigned to different optical frequency bands, as well as spatiotemporal beams, where different spatial and polarization states are assigned to different delays. First up, we've got a spatiospectral example. With this device, we can map any arbitrary spatial and polarization state to any frequency band. So there's a lot of options. I'll cut to the chase here and just show a relatively sophisticated example before moving on to spatiotemporal beams. Here we're looking at an example where different letters of the Latin alphabet are assigned to different frequencies. Each character is separated by 50 gigahertz, with the horizontal polarization cycling through in alphabetical order and the vertical polarization in reverse alphabetical order. So we've got all degrees of freedom going at once here. Relatively complicated spatial states being generated independently for each polarization at each wavelength. We are controlling the spectral phase in this example, but it's being kept essentially constant in these animations. So all the letters are green. They're all the same flat spectral phase. And that flat spectral phase means that almost all the power that makes up these characters all arrives at the same delay. If we look at these same results in the time domain rather than the spectral domain, that's what we see. Moving on, we're mostly going to focus on spatiotemporal examples. And the idea is essentially the same as spatiospectral examples, except the targets are specified in the time domain rather than the spectral domain. And in general, it means we're going to have more complicated control over the spectral phase. We'll start with what is essentially your classic time reversal type demonstration, the generation of a spatiotemporal focus. Here we have a horizontally polarized, diffraction-limited spatial focus generated at 0 picoseconds with a bandwidth-limited pulse duration, which is about 230 femtoseconds. A pretty simple example, really, compared with the kinds of things this device can do, but nonetheless one which requires full control of space, polarization, and delay. For all of these, I've zero-padded the frequency domain in these animations by a factor of 4 for clarity, so each frame of the video is 56 femtoseconds. In this example, the focus spot is linearly polarized at 45 degrees. If we look at the volumetric plot on the right, it is focusing to a small spot at 0 picoseconds, but it isn't very clear due to just the sort of format of the plot. We can also shift the arrival time of the pattern. This is a linearly polarized at 45 degrees focus, same as the previous example, but at a delay of 4 picoseconds. And now we can actually see it on the volumetric plot because it's not obscured by the axis labels. In the previous demonstrations we just saw, we've been generating a spatiotemporal focus. Essentially, all the light arrives at one place at one time. This one I'm calling a smiliotemporal focus. We've got a smiley face in the spatial domain of bandwidth limited duration in the time domain, offset to 5 picoseconds. So similar ideas to the previous examples, except the spatial pattern is more complicated now. It's not just a spot, it's a smiley face. Now, smiley face is actually a little bit tricky to generate with only 45 spatial modes. You really need to make sure that all of those modes are addressable and working quite well if you want to get a proper smiley. Or, rather than a focus spot, we can generate something with some spatially dependent polarization structure to it, like a vector beam, a radially polarized donut in this case. Next, we'll play more along the time axis. Rather than generating a single pattern at a single delay, we'll be generating different spatial patterns at different delays, right? So filling up that time axis. This one is a focus spot, linearly polarized at 45 degrees, that traces out a spiral trajectory in time between plus and minus 10 picoseconds. So if you imagine when this beam is collimated, the time axis is effectively just the spatial z-axis. And if you could see the spatiotemporal beam flying through space at a particular instant in time, you'd see this funny shaped conical corkscrew-like beam. Here we have a circularly polarized focus spot that's raster scanning across the entire core of the fiber through a time interval of plus and minus 10 picoseconds. This example is the same, except over a plus or minus 20 picosecond interval. It's harder to deliver light to large delays, mostly because it requires the SLM to steer to larger angles along that temporal axis, along that spectral axis. And we'll talk about that a bit more later on with some delay-dependent loss tests. But at plus or minus 20 picoseconds, it's still holding on okay, particularly on the negative delay side. Going over a longer time period, plus or minus 40 picoseconds, at 80 picoseconds of total delay, we're talking about a spread of about 24 millimeters of free space distance. So we would have to be careful that we're not clipping on the edges of any optics like prisms, but really it's more about the spectral resolution of the beams on the SLM and the spatial resolution of the SLM. To do these long delays, you need to apply a lot of phase gradient as a function of frequency. So you need beams that are spectrally narrow on the SLM and pixels on the SLM that can transition effectively from one pixel to the next to actually apply that phase gradient. Again, we'll get more into that into some of the later tests that we'll talk about. But really at 80 picoseconds of total delay, it's too much for this particular device. But it would be an achievable amount of delay, with some further tweaks. This example is supposed to symbolize a clock hand in the time domain. We've got this line going from the core of the fiber to the cladding, which rotates around as a function of delay. So one polarization has an arm rotating clockwise and the other polarization rotates counterclockwise from minus 10 to plus 10 picoseconds. 3 rotations in that 20 picosecond interval. Here we have the two polarization components working cooperatively together to generate a radially polarized clock hand. So there's 4 rotations in the 20 picosecond time interval, but the amplitude and phase of the horizontal and vertical components is always such that the polarization vector is linearly polarized and pointing outwards along the clock hand. In this one, it's rotating faster and has a different number of rotations in each polarization. Horizontal does 10 rotations in 20 picoseconds. Vertical polarization does 7 rotations in the opposite direction in 20 picoseconds. Rotating faster still, this is 15 rotations per 20 picoseconds in opposite directions for the two polarizations. Here you can actually see the temporal resolution of the device, as the clock hand really does more of a tick-tock discrete motion from one 230 femtosecond time interval to another. The clock hand position has moved enough that it's no longer a smooth motion. You can really just see it tick, 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 tick to those discrete positions. Because of the optical bandwidth of this device, we can't manipulate anything on a time scale less than about 230 femtoseconds. An example over a shorter time interval now, with some more complicated spatial patterns. We have numerical characters, vertically polarized, arriving 230 femtoseconds apart across a plus or minus 4 picosecond time interval. For this one, we have Gaussian modes in both polarizations being generated at adjacent time intervals. So every time interval is completely orthogonal with every other time interval. So that is that the spatial field has to completely transition from one interval to another. So unlike examples for, say, the slow-moving spots or the letters or the clock hands, even for some of the fastest rotating ones, there's always a little bit of overlap between the spatial fields from one time interval to another. This one requires a completely orthogonal field every single time interval. We'll actually go through later on and do some even harder examples later on to really stress the system. Of the demonstrations so far, some, like the spatiotemporal focus, represent a beam type that's of practical interest. Other demonstrations, like the generation of LG modes at adjacent delays, probably has little practical use, but it is of technical use in terms of quantifying what the device is capable of. And then there's ones in between, like the clock hands or the raster scanning or the numbers, that are partly practical, partly technical demo, and partly for fun. And then we have demos like this. We call it the arrow of time. It's a 20 picosecond long 3D optical field that's literally shaped like an arrow that points in the backwards time direction. So if we were watching this beam in reverse, it'd look like an arrow which flies out of the camera and back towards the multimode fiber and the source. So in the time forward world in which we live, that means the arrow flies in base first and arrow tip last into the camera. Practical applications of such a beam? None. Technical merits of such a beam? Also none. Fun of such a beam? Max points. We don't know of anyone that needs such a beam, and it's actually a pretty poor way of testing the device. And it'd actually be kind of stupid to use a device like this to generate such a beam, even though we did. The changes in time are actually very slow, which means that the bandwidth of our pulse is actually very narrow. So remember, for all these tests, we're coming in with a 230 femtosecond pulse equivalent, right? Full bandwidth of the device. And then in this case, that means that we're just throwing most of it away because the final shape has no features on that time scale. You can actually see the zero order of the digital holographic reconstruction at the 6 picosecond mark because the power is getting low because we actually threw away most of our pulse. However, what this demonstration lacks in usefulness or technical interest, it makes up for in sheer joy and gimmickry. In a similar vein, we've got our Eiffel Tower demonstration. It's a 12 picosecond tall tower that flies into the camera base first. Again, no practical use case and pretty useless as a characterization or diagnostic, but it's a lot of fun, and it's also supposed to be a bit of a homage to previous work at the Langevin Institute, such as in water waves, where they use the Eiffel Tower as a test case. Okay, so moving on from the fun demonstrations, now we're going to look at some tests that are all business. Characterizations of the device, looking at what it's capable of, what its defects and limitations are, and what the best and worst case scenarios are. Like I've tried to emphasize a few times, we're doing these experiments using a transfer matrix approach, and one of the benefits of that is the completeness of the characterization that you get. So not only can we generate all kinds of different beams that we don't have to physically backpropagate first, it also means that using linear algebra techniques, we can find the absolute best and absolute worst case scenarios for the device. If you just backpropagated a bunch of states of interest, you'd never find these worst case scenarios. You really have to have the transfer matrix and do the singular value decomposition. In these results, we're looking at the transfer matrices of the device as a whole, which includes the attached multimode optical fiber. However, the multimode fiber is effectively lossless. First up, here's the insertion loss and mode-dependent loss of the device. The insertion loss is the average singular value of the transfer matrix, and the mode-dependent loss is the ratio between the maximum and minimum singular values. So mode-dependent loss is also known as the condition number of the matrix, and it describes how invertible it is. I've done an in-depth explanation of the singular value decomposition and the concepts of insertion loss and mode-dependent loss, and how they relate to a device like this in the video for the Gaussian mode sorter, so I won't repeat that here. Long story short, insertion loss is the average loss over all possible mode superpositions through the device, and the mode-dependent loss is the maximum loss difference between any two superpositions of modes through the device. The insertion loss is between 17 dB at the best frequency and about 20 dB at the worst frequencies. The breakdown of that loss is 3 dB of polarization dependent loss due to the static polarization beam splitter in the setup. We're taking the harshest definition of loss here. We're assuming that one polarization component of the SLM is being used and the other is being completely discarded. So there's always a loss there. So in practice, it's an unlikely scenario to occur. Typically, when there's scattering in a multimode fiber involved, the answer you need to generate on the SLM tends to be closer to 50-50 in power between the two polarizations. But theoretically, the worst case is you have to just turn off power on one side of the SLM entirely. Actually, even in that case, you'd really just adjust the input polarization to the device with the pole controller at the input. The really worst case would be that you need to generate all H, then all V, then all H, then all V in adjacent frequencies on the SLM. Then you'd have to incur the 50% loss. and you couldn't easily just realign your input polarization to get around it. Anyway, summary, like we do throughout a lot of these tests, we assume the worst case, even though the worst case is actually pretty unlikely to ever occur in practice. So 3 dB of polarization dependent loss. Next, there's the multiplane light conversion system. That's got about 5 dB of loss. 2 dB of that is due to 14 reflections off the gold of the phase masks. The device itself has about 1 dB of insertion loss, even theoretically, due to just scatter. And then the other 2 dB is from other imperfections, like misalignments, scattering off the pixel structure, and coupling in and out of the device. The remaining 9 dB of loss is for the spectral pulse shaper subsystem itself. With some realignment, more optimized optics and more tweaking of things like the phase masks, that could be improved. For reference, a commercial multi-port spectral pulse shaper like a Finisar wave shaper 16000A, which supports 19 ports, they're currently sold as having 5 dB of insertion loss. And that kind of loss could be achievable for a device like this, even though it's got more than double the number of ports. So with some further tweaks and redesigns, you could get rid of that 3 dB of polarization dependent loss, which I'll also talk about a bit later. You could potentially make the multiplane light conversion system with dielectric reflections instead of gold. That would buy you another 2. And then optimizing the spectral pulse shaper itself would get you down another 4 dB for a total of about 8 dB total loss. A more optimized device should be capable of something around that. And of course, chipping away at losses in your design and build is a game that you can play from now until the end of time, right? Looking at mode-dependent loss now, if your application is power limited, then insertion loss is going to be one of your big concerns. Mode-dependent loss is related to how orthogonal your addressable spatial and polarization degrees of freedom really are. So it's related to the quality and the complexity of the beams that you can generate. So infinite mode-dependent loss would mean we don't really have 90 spatial and polarization channels. We've got at best 89. At least one channel has infinite loss and doesn't really exist. You'd have to look at all the singular values for the full picture, but that's the kind of basic idea. We've got a mode-dependent loss of between 7 dB and 10 dB. And that's actually pretty good for a measurement of a 90 mode device. I usually have to put this in context because people often don't look at mode-dependent loss plots. But for example, it's not uncommon to do a measurement of a piece of multi-mode fiber patch cord, which supports 90 modes using an SLM and a camera, and end up with a measurement that has 4 or 5 dB of mode-dependent loss. And that's for a device which is lossless, right? Just a patch cord. It's a very harsh measurement, and it always finds the worst possible case scenario. So you really can't hide anything from it. Probably plots that are a bit more intuitive if you're not used to doing the single value decomposition and working with mode-dependent losses is to take a look at the transfer matrices multiplied by their complex conjugates, so the time reversal operator. This gives you similar kinds of information, measures of how orthogonal the channels are and how much loss they have. So if our device was ideal, we'd have transfer matrices which were unitary, so that is lossless. Or perhaps more realistically, the device might have some overall loss, but it's a loss that's common to all modes, all possible combinations of modes through the device. No mode has more or less loss than any other. They've all just got the same common loss. A perfectly invertible matrix with a set of 90 identical singular values. It'd mean that the transfer matrix multiplied by its conjugate transpose would be the identity matrix to within the overall loss. A diagonal matrix where all the diagonal elements have the same value and all the off-diagonal elements are 0. If you want to think of it physically, we propagate through the device with the transfer matrix, then we backpropagate it with the time reversed matrix, its conjugate transpose, and then ideally we would end up in exactly the same state as we started the identity matrix. If we look at the time reversal operators that we've measured for the best and worst case frequencies, we can see that the results are indeed very diagonal, but if you look closely, there is some crosstalk in the off-diagonal elements, meaning the columns of our original matrix were not completely orthogonal. And there's also different amplitudes along that diagonal, meaning not all addressable channels have the same loss. This plot breaks down the losses of the different addressable modes of the device. All of these results are sorted in terms of the Hermite-Gaussian modes excited at the input of the multimode fiber. The first 45 modes are in the horizontal polarization, and the next 45 modes are in the vertical polarization. Now, because of the way the 1D array is mapped to the 2D Hermite-Gaussian modes, This means that mode 1 and mode 2 are not adjacent positions in the 1D array. They're adjacent modes in Hermite-Gaussian space, not that linear array space. Looking at this plot, we've got about 5 dB of differential loss between the best and worst Hermite-Gaussian mode at a given frequency, a number that stays relatively constant across frequency, but there's a 4 dB roll-off in the overall loss across the frequency band. Remember, mode-dependent loss was about 7.2 dB, whereas in the Hermite-Gaussian basis it's only 5 dB. So remember, the mode-dependent loss finds the worst-case superpositions of these Hermite-Gaussian modes. This plot's basically the same as the previous, just organized in a different fashion. Probably the most notable feature is there's extra loss for mode 37 and the corresponding mode in the other polarization, mode 82, which implies that extra loss is being introduced by the multiplane light conversion system. Now, those previous plots were all about looking at how the performance depends on spatial mode and frequency. In the next plots, we're going to look at how the performance depends on delay. This plot's a measure of the impulse response for each of the 90 input modes to the device. The top 45 in the plot are the horizontal polarization and the bottom 45 are the vertical polarization. Again, we're working in the Hermite-Gaussian basis. There's contributions to these impulse response both from the spectral pulse shaper subsystem itself and also the multi-mode fiber. The MPLC subsystem shouldn't really have any mode-dependent delay, at least none that's resolvable within the bandwidth of the device. If we take a look at the total impulse response over all modes, we have something like this. It's about 2.5 picoseconds worth of delay, and that's composed of roughly equal contributions from the spectral pulse shaper subsystem, mostly residual path length differences between the two polarization components within the device, and the group delay spread of the modes in the multi-mode fiber. So the SLM has to undo this impulse response, plus add whatever spatiotemporal features are required to generate the desired output spatiotemporal state at the end of the multi-mode fiber. Next, we'll take a look at the delay-dependent loss. So we looked previously at the spatially dependent loss, the fact that different spatial and polarization modes have different losses, but with the spectral pulse shaper, different delays also have different losses. There's a few different mechanisms. You can think of them as 2 or 3 different types. First, there's delay-dependent angle to the beam. That means a loss of coupling to the 1D array of the MPLC. If we're introducing delay, that means we're entering the lens over here from the side, which means that we'll end up coming in at an angle over here at the MPLC. Second, there's the fact that when your beam is delayed, that means it's traveled a longer distance, and if the beams are relatively small, like we have here, that means they'll get a little bit out of focus, depending on the delay. And you could compensate for that, but really, for our device, the delay-dependent loss that dominates is diffraction efficiency. Creating long delays means steering light at large angles in the spectral direction with the SLM. It means we need to apply phase gradients that change rapidly as a function of frequency, which in turn means we need high spectral resolution on the SLM. That is, we need the beams on the SLM to be narrow in the spectral direction, but we also need the SLM itself to have enough spatial resolution with its pixels to actually apply the required phase gradient. For this test, we're generating a horizontally polarized diffraction limited spot at 0 picoseconds. We're also generating a vertically polarized diffraction limited spot at a different spatial location but a fixed location, and then changing the arrival time of that vertically polarized spot. So 2 spots, one's at 0 picoseconds, one's at some other delay, which we move. And then we look at how the loss changes. So we get something like the field we're looking at here on the top. Now, as the delay changes, the total power drops. Power is normalized to 0 picoseconds. We naturally get double intensity per time slot when H and V are at 0 picoseconds. So for all other delays, the ideal case would actually be 0.5. We can see that there's a roll-off, and it's asymmetric. Negative delays perform better than positive delays. This could be due to asymmetry in the diffraction efficiency of the SLM. Due to the non-ideal behavior of liquid crystals, they'll be able to diffract more efficiently in some directions rather than others, depending on how the liquid crystals are aligned. Or it could also be due to some other misalignment in the system, which is biasing the loss at slightly negative delays. So it corresponds to about 1.8 millimeters of path length in air. Alright, the final set of tests we're going to do here are aimed at really pushing the device to its limits and really throwing the worst case scenarios at it. To be fair, These scenarios are pretty unlikely to ever actually come up in practice. The scenarios we've designed deliberately to be very difficult for the SLM to generate, as they require steering light with equal intensity to all spatial and polarization modes at all frequencies, with mode superpositions that keep changing to different orthogonal superpositions between the spectral components. So that is a lot of spatial frequencies in the spatial direction of the SLM, and also a lot of spatial frequencies in the spectral direction. All the spatial and polarization ports are always on with equal power, but they're also always changing as a function of frequency. To test this, we'll be trying to implement columns of the n equals 90 discrete Fourier transform matrix as a function of frequency. The important property here is that all the spatial and polarization modes have magnitude 1, but the phase is such that every column is orthogonal to every other column. So the change from one spectral component to the next requires the state to change to a completely orthogonal spatial and polarization state that has no overlap with the adjacent frequency bands. This is that goal. For our first test, we'll be working with frequency bands approximately 50 gigahertz wide, which means there's 90 across the 4.5 terahertz of the device. This is coincidentally means we've got the same number of spatial and polarization modes as we do spectral bands for this particular 50 gigahertz example. But as we start going to narrower spectral slices, we'll start to repeat the matrix columns several times. The spatial polarization states we'll be generating as a function of frequency are not of interest unto themselves. Their only point is to be difficult for the SLM to accomplish. Ignoring some calibration terms for the performance of the spectral pulse shaper subsystem itself, like PMD, these spatiotemporal states and their corresponding spatiotemporal states are being generated at the input of the multimode fiber. The point here is to demonstrate the ability to transition between a sequence of precisely defined but ultimately pointless states as accurately as possible. The frequency bands are specified as 1 to 5 samples of the digital holography characterization apparatus. The resolution of the characterization apparatus is 10.067 gigahertz. So our first test of 5 samples wide is 50.3375 gigahertz. I'll just be referring to them as 10, 20, 30, 40, and 50 gigahertz in this discussion. For a given goal spatiospectral state, the corresponding phase mask is calculated to approximate that state. So no attempt is made to equalize the amplitudes. There's a theoretical loss you can't get around with a single phase mask, which I mentioned previously, and I'll talk about more in a moment. On the far right here, we've got the scenario corresponding to all modes being generated in phase, and we can see that the loss is poor for that scenario. This is the worst case scenario. It means all the spots in the 1D input array of the MPLC must be generated of equal amplitude and in phase, which when you look at the Fourier transform of that in the plane of the SLM, means the corresponding field is a very small spot on the SLM, much smaller than the illuminating beam coming from the source. That size mismatch means that you must incur loss. In this case, it can't be better than about 14%. To do better, you'd have to use at least 2 phase planes. Our DFT is being implemented in the basis of the Hermite-Gaussian modes at the output of the MPLC, but if you were implementing our DFT in the basis of 1D spot array at the input of the MPLC, every column would be like that. We'd have the absolute worst case scenario for every spectral component all the time. For these tests, we'll be generating columns of the DFT matrix in the Hermite-Gaussian basis at the input of the multimode fiber, and then at the other end of the multimode fiber, where we actually measure the field, we'd expect to see this, given the optical transfer matrices that we've measured. Here's experimental runs for 50 to 10 gigahertz wide spectral transitions. The top is the ideal fields we'd expect. The middle are the measured fields, and the bottom is the difference between the two. It's really too much to take in as a single plot, and I'll simplify it in a moment, but we can see that the transition is slow as a function of frequency over on the left and fast over on the right. For the 50 gigahertz bands, the difference field is dark most of the time, meaning the ideal and measured fields are the same most of the time, and the difference field is hence dark most of the time. That periodic flash of field in the difference is the transition occurring from one band to the next. In the ideal case, the change occurs instantaneously between the states, whereas the real device will have to transition over some finite bandwidth due to the spatial resolution of the SLM and the width of the beams on the SLM in the spectral direction. Over on the 10 gigahertz side, The device really just can't keep up at all. It doesn't have the spectral resolution to change on the scale of 10 gigahertz. So there's basically always a difference field. It's just constantly blurred out in the spectral dimension, unable to implement 10 gigahertz wide transitions. We'll look at that in more detail in a moment, but the point of these slides is really just to put in your head what exactly it is that the test is measuring. This is the ideal spatiospectral state at the output of the multimode fiber for 50 gigahertz bands. Ideally, we'd measure exactly this on the camera side. It looks random on this end, but it corresponds with the DFT at the input. Then on the output side, we experimentally measure this. The two are closely correlated at the center of the band. It's clearer to look at it like this. This is the normalized overlap between the ideal state and the measured state for each frequency. 1.0 means the states are identical, 0 means they're orthogonal. The green trace lets you follow by eye the correlation between the ideal and measured at the center of the band. And then in red, we see the full trace, where we can see all the dips. Those dips are the transition points between two adjacent frequency bands where the spatial state must change between two orthogonal spatial and polarization states. Again, if the spectral resolution of your measurement apparatus is higher than your device you're measuring, you'll be able to see those transitions. So in band, the correlation is approximately 90%. Ideally, we'd expect about 95% because that's the quality that we specified in the Gerchberg-Saxton algorithm to calculate the masks. We can also look at the correlation in the time domain. As we test the spectral resolution of this device and keep pushing to narrower and narrower frequency bands, we're also testing the ability of the device to generate larger and larger delays. In the time domain, we can see there's a close correlation between the ideal impulse response and the measured impulse response, with some additional loss at the positive delays relative to the negative delays, consistent with what we saw in the delay-dependent loss test from earlier. There's small features out at plus or minus 30 picoseconds, but this device isn't really able to generate them, especially on the plus 30 picosecond time. But this will be more obvious as we increase the spectral resolution of the test. Going now to 40 gigahertz. Now that worst case in-phase column is inside the bandwidth of the device, so we're going to be able to see it. Last time it was at the edge of the operating band at 195.5 terahertz, so we didn't really get to see it in action. Here we have ideal theoretical coefficients generated by the mask, with the low efficiency in-phase worst case here. Ideal spatiospectral state, measured spatiospectral state, correlation between the two. Still pretty good at mostly between 80 to 90%, but we can see a bit of a dip here at that in-phase absolute worst case scenario, but even that's about 75% correlated. In the time domain, we've got good correlation between the ideal and measured impulse responses. Again, for delays up to about plus or minus 10 picoseconds, still not too bad at plus or minus 20 picoseconds, but pretty degraded outside of that. And then we can just keep going. 30 gigahertz wide bands, still holding on with good correlation. The worst case in-phase scenario struggling a bit more now at like 65% correlated, but otherwise we've got mostly values between 80 and 90% correlation throughout the band. Impulse response is getting longer and longer, and the discrepancy on the positive delay side is becoming more obvious. At 20 gigahertz now, I'd say this is really the point where things start to break down. The size of the beam on the SLM is about 15 gigahertz, so we're coming up against that limit at the very least, if not the SLM itself. Correlation is about 70 to 80% throughout the band, except for those worst case in-phase examples. There's two worst cases now, because we're cycling through the DFT matrix 2.5 times. Looking at the impulse response, most power at longer delays, actually not that bad at the negative delays, but positive delays are definitely struggling out past about 10 picoseconds. Then finally, 10 gigahertz. Now the device has basically failed to keep up with the spectral resolution of the transitions being requested of it. Changes of 10 gigahertz means about 2 pixels wide on the SLM. So we'll have a lot of diffraction efficiency issues, even aside from the fact that the beam is 15 gigahertz wide. There's poor correlation in the frequency domain. The transitions basically never finish before a new transition starts, leading to correlations around the 40 to 50% mark. And then the time domain, there's really no ability to generate any features out at those 30, 40, 50 picosecond delays. Now I'm going to talk about scalability of this kind of device. I think an important point is that there's multiple routes towards scaling up the performance in both the spatial and the temporal dimensions by adding SLMs in essentially every direction, both transverse and longitudinal to the optic axis. Because ultimately, if this device was such that you would always have to do everything using an SLM, a single SLM, then eventually you're going to run out of pixels in practice. And when we're using a standard HD panel here, you could move to 4K pretty easily, but SLM technology largely follows display technology, so I wouldn't expect the number of pixels on a single panel to grow much beyond that over time. We've gone with what is really the simplest possible implementation, the implementation we think it'd be easiest for others to duplicate. We've split up the H and V polarization components onto the left and right side of the panel, so each polarization only has to address 45 ports each. An alternative implementation is to come in with a single beam that addresses 90 ports, half of which would be H and half of which would be V, either interlaced or in two separate blocks. That'd be a better approach in some ways. It could potentially be a lower loss, as the overall polarization splitting is programmable now. Downside is you're asking more of the spatial resolution of the SLM in that Y direction. So in this case, we went with the more conservative route of splitting the SLM horizontally, which trades off some resolution in the spectral dimension to effectively gain some in the spatial dimension. For the first demo, we were more interested in making sure we got all the spatial components rather than tweaking things like loss and that kind of stuff. Of course, you could also just process the two polarization components on separate SLMs entirely and double the number of addressable pixels. But, that's a relatively minor change and a relatively easy one to do. Along similar lines, you don't have to process all the spatial modes on a single SLM. And as you add more modes, it'll actually become easier not to. Doing it all in one SLM is hard for two reasons. One, the SLM itself. It'll find it increasingly difficult to address all the ports accurately, if at all, the more ports you add for a given SLM resolution. But the other is actually the MPLC. Just by its nature, mapping a 2D space to a 1D space doesn't scale that well. You're mapping an area effectively onto a line. So whereas the beam size might only grow with like square root n, the line it maps onto is just going to grow linearly with n. You can do it. Here's an MPLC device for 135 modes, still mapped onto a line, but ultimately you end up adding many planes roughly linearly with the number of modes. But as we've shown in previous work, you can also map onto a 2D grid of spots, much easier, and that actually scales much more gradually. So these are MPLC designs for 210, 1035 spatial modes, and they actually use less modes, or less planes, than the 135 mode 1D mapping device that I just showed before. By default, these type of transformations map most easily onto an equally spaced triangular array, but you can also just add a couple extra planes to map it onto a rectangular grid. That's not a big deal. And then divvy up the columns of the array to different SLMs. Or an alternative is you could use something like a laser-written waveguide to map from the triangular array to a line, rather than asking the diffractive optics to do all the work. You could do a fixed split amongst the columns with static optics, or you could use an SLM to make it programmable. So I'm talking here about splitting up the spatial or polarization degrees of freedom amongst different SLMs in the transverse plane. But you could also add more SLMs to scale it in the temporal dimension, the longitudinal direction. In our design, we do a 45-way split for each polarization using a single SLM. That single SLM has to make each spot have the correct amplitude and the correct phase. And that also introduces additional loss because it necessitates some discarding of light, as is the case in general when you're trying to match amplitude and phase using a single phase mask. An alternative is to use two SLMs. The first does the amplitude split the best it can, the second fixes the phase of all the modes. And then you could also abstract that even further to make it something more like an MPLC type system, not strictly amplitude and phase in the two planes, but just n planes of phase manipulation which implement a given transformation. Another way to increase the number of addressable degrees of freedom by spreading the load amongst multiple SLMs. The point here is that there's lots of extensions to this work that could see it scale in both the spatial and temporal dimensions. Some are easier than others, but ultimately this is all about putting existing components that we already know how to build together. It requires good optical design assembly code to drive it, but it doesn't hinge on some new technological breakthrough to be invented or anything like that. It doesn't require a 1 gigapixel SLM to suddenly become available or something. Another point is we've built this device for the telecommunications band at 1550 nanometers, but there's no real reason you can't build this at any other wavelength. There's nothing particularly special, nothing particularly that ties it to 1550. As long as you've got an SLM that works in the wavelength band you want, everything else is mirrors, lenses. MPLC is also not really wavelength specific. So you could implement this at other wavelengths, and of course spectral pulse shapers already exist at these other wavelengths.